This is an introduction to current carrying capacities and voltage drop calculations for copper conductors. So, first and foremost, current carrying capacity is based around these calculations here. We've got IN has to be less than or equal to IB. Now IB is where we start. This is our design current. So if we have a design current of 32 amps, then the IN is the overcurrent device the rating of the overcurrent device. So if this is 32, then this can also be 32 because there are MCBs, RCBOs and such that are rated to 32 amps. If this one's 35 amps, then IN is likely to be 40 because that's the next common size of overcurrent protective device that is available. So this is the design current, that's what the device connected is going to use. This is the size of the overcurrent protective device. We then have IT. Now IT here is the tabulated current carrying capacity of the cable. Now we take this from BS7671. So there is a table within BS7671 that has the tabulated values for how much current each cable can carry, which is this. And in order to work out whether the relationship between our overcurrent protective device and our tabulated current, so the tabulated current has to be the same as or less than the overcurrent protective device, because there's no point in having a 32 amp overcurrent protective device if the cable can't carry 32 amps. So this amount has to be less than this amount. So what we do is we take this number, so say for argument's sake 40 amps, and we'd put that in above, and then we have these values here. Now CA is for ambient temperature, CG is for grouping of cables, CI is for insulation, so thermal insulation that will affect the cables, and CF is for the type of protective device. So for argument's sake, if we had a BS7036 semi-enclosed fuse, that would derate the circuit as well. And these are just derating factors. If the cable can't dispel heat properly because of thermal insulation, then we need to take that into consideration. The more insulation you have, the more this will affect the circuit, and the more that will bring down the current carrying capacity of that cable. So where there is no grouping, for argument's sake, or if there's no insulation, if the cable is clip direct, we just use 1 for this value. If there is a factor to take into account, again, these values are just taken from BS7671. So although this might look complicated, in order to find most of these values, it's either what size device are you fitting, or they are known values taken from BS7671. What might this look like then? Well, if we've got a design current, an IB, which is 32 amps, then our IN, which is, remember, our protective device, so the device we're going to install, well, 32 is a fairly common size, so we can fit a 32 amp in there. So the next bit is IT, the tabulated value. Now, in order to find that, we need to know our IN, which goes at the top there, and then we need to add our cable derating factors. So we now need to add our derating factors, so that's these here. Now CA is for thermal effect, so ambient air temperature. So an ambient air temperature other than 30 degrees, if it's 30 degrees, then we just put a 1 here. Ambient air temperature of 25, which is more common in the UK, will allow us to add in a factor for a 70-degree thermoplastic cable of 1.03. And if we remember from maths, when these figures are just next to each other like that, it means that they are multiplied together. The grouping factor, which is CG, we're just going to use as 1 for now. The CI, again, we're going to use clip direct, so 1. There's no of that, and it's not a 3036, it's a normal RCBO or something along those lines, so that will also be a 1 there. The only time really that this factor is taken into consideration is if it is a BS7671 rated 3036 semi-enclosed fuse, which are the old-fashioned put a wire in type fuse connection, and then that one gets a rating factor of 0.725. So it's either a 1 or it could be 0.725. So that's the only time, and that's if it's a semi-enclosed fuse. So what we've got now is our calculation here. So we need to do 1.03 times 1 times 1 times 1 times 1, which means that we're going to end up with just 1.03 on the bottom, and we'll do 32 divided by 1.03, and that will give us our IT value. This means IT is equal to 31.0679, carries on, 612. So IT, for all intents and purposes here, 31.07 would be fine, and that's in amps. Now, we can see that our IT has to be greater than or equal to IN. Well, IN's 32, and this one is 31, so with our derating factors, so that's absolutely fine. We're now going to go to our table in BS7671 and look up what cable is capable of carrying 31.07 amps. It won't give us an exact value, but it will give us a value that is either exactly this, or we need to look for the next size up of conductor that can carry this. This table, which is table F6 or table 4D5, so table F6 is in the on-site guide, table 4D5 is from BS7671. This is for twin and earth flat cable. If we were wanting to do this circuit in flat cable, we look for where can we see 31.07. Well, we won't be able to see 31.07, but we've got 34 here. We've got 27, 35. So we're looking here. The cable above that, which is 4 mil, so the number of millimetres is the cross-sectional area of the cable. That's the size of the cable there. 4 mil. We can see from this row here, if it's clipped direct, 4 mil would be absolutely fine. But if it was any other method, so if it's enclosed in conduit on a wall, if it's in a stud wall with insulation touching the inner surface, above a plasterboard ceiling, any of those, 4 mil would not be sufficient, and we would have to go to the next size up. So, and again, we can see if our reference method is 101, even 6 mil cable wouldn't be big enough, because there would be so much insulation there that the cable wouldn't be able to dispel the heat, so it can't carry as much current, and we'd have to go up to the next size again. So you can see that a 10 mil cable, which is reference method 101, can carry 36 amps. But for ours, we said there's no grouping, there wasn't any grouping, there wasn't any thermal insulation. We said it was going to be clip direct, so we come down this column here for the clip direct, and we get to 37. 27 is not big enough, so we go to the next size up, 37, and that is a 4 mil conductor. Now, that is the size of cable that we can use, but it's not where we end our cable calculation. We now know what conductor can carry this if it is installed this way, but we also have to factor in the length of circuit, because voltage drop will become a factor, and that's what this is here. We've got the voltage drop on the end here, and so we need to do a second calculation now in order to work out whether the conductor needs to be a larger size to combat any potential voltage drop within that circuit. So the voltage drop calculation, which is the second one we need to do, looks like this. So here we have voltage drop is equal to, and then we have this here, which is actually just the values taken from here. So again, we're just taking a look at the calculation and we are then inserting information from BS7671. There's no requirement for anyone to remember any of this. These formulas are all in BS7671 and all of the values that you need are taken from these reference tables. So this one, and then we've got IB, well that we've agreed on earlier, that's our design current, and then our length of circuit is here, and then the whole lot is divided by 1000 to give our voltage drop. So for the circuit that we've been working on, this here, we go for 4 mil, we go across, that figure is going to be 11. So inputting those data, we've got 11 from our table, which we put here. So this, go to our table, is 11, put that in. Our IB, our design current, we've already said was 32 amps, so we're going to stick that in here. The length is in meters. I'm going with 50 meters. It's quite a long circuit, but even in a domestic setting, this is a very achievable length of circuit. They can easily be longer than that. And then we've got our divided by 1000. We calculate that, and that will give us our voltage drop. So if we perform this calculation, we do the multiplications along the top first, and then we just divide by the 1000. Gives us a voltage drop of 17.6 volts on a 4 mil conductor. Now, this actually presents a problem. So there are tolerances, allowances for voltage drop. Now, if we use a 4 mil conductor, we know it can carry the current, but if the circuit is 50 meters long, we're going to experience 17.6 volts of drop, or voltage drop, in this circuit. Now, if it's a lighting circuit, our maximum allowance is 3% or 6.9 volts. For any other type of circuit, such as a socket circuit, it's 5% or 11.5 volts. So that means that actually, although 4 mil cable can carry the 32 amps of current based on a reference of C and using our derating factors and all that type of stuff, it fails based on voltage drop. This voltage drop is too high. So how do we remedy that? Well, once again, we would need to choose a larger cross-sectional area. So although clip direct 4 mil is adequate, with the voltage drop it won't be, so we need to go up to the next size up. So actually, the 4 mil is no longer acceptable. It would have to be a 6 mil cable. So that's 6 mil CSA, cross-sectional area, twin and earth, and it would be reference method C. And that would be the correct cable for this circuit. So in order to have a 32 amp circuit that is 50 meters long with a reference method of C clip direct, it will have to be a 6 mil cross-sectional area cable if it's twin and earth. There are different tables throughout BS7671 for the different types of cables. So if it's armoured cable, these values are all different. So you can't base an armoured cable circuit on the table for twin and earth flat cable. So all this information at the top here, 70-degree thermosetting plastic flat cable, that's just basic twin and earth. And you can see here we've got an ambient temperature of 30 degrees for these values, which is why we add our derating factor of 1.03, because actually the ambient temperature in the UK would be usually less than 30 degrees. If your cables are for a lighting circuit and they're going to be in a loft where we know that the temperatures are higher, it might be worth leaving them at the 30, and then that would be a 1. If you think actually it's going to be in a greenhouse or something like that, or I mean in lofts it is hotter too through the summer, you might want to add a derating value, again taken from the on-site guide or from BS7671, that will derate the cables further. But that is a basic introduction to how we calculate the correct conductor size for our cables.